hello everyone, I'm Benjamin from Osaka University and RIKEN. So today we have the pleasure to welcome Pierre Alquier, so who is a research scientist at RIKEN AIP at the approximate Bayesian inference team. So his research interests go from time series, high dimensional statistics to Bayesian inference. And so today's talk is dedicated to exponential deviation inequalities for Markov processes. So if you have any question during the talk, please feel free to ask them. So you can, what I propose is that you write them down in the chat box, and I will inform Pierre about your questions. And I think Pierre will be happy to answer them. So I think Pierre, you can start. Thank you.
Okay, well, first, thanks a lot to Benjamin and to Makoto for the invitation and for the introduction. So indeed, I'm in the approximate Bayesian inference team in the Nihonbashi campus in Tokyo, but I'm like for once today, I'm not going to talk about Bayesian methods at all. I'm going to talk about deviation inequalities for Markov chains. So first, I want to introduce my co-authors, Xiequan Fan from Tianjin University and Paul Ducamp from Cergy-Pontoise University. And the paper actually I'm going to present is here. So, and the slides are on my webpage. So if you want to find the reference, you can just easily download the slides. So the whole talk today is going to be about deviation inequalities of the following form. Like just to try to understand how much an empirical mean can deviate from the corresponding expectation. Okay, I must say that, of course, such results are quite classical, at least for independent observation. They are quite classical in probability and in statistics. And you might agree, I assume that many of you, most of you know some results to do that kind of things. On the other hand, it might very well be that some people don't actually know some of these results. So in order to make the rest of the talk easier to follow, I will start by actually a very short introduction on such inequalities, starting by the most obvious ones like Markov inequality and Chebyshev inequality. And sorry if it's like if it seems very, very easy and well known to some of you, but actually I will use this to build on more sophisticated results later. Actually, okay. So let's start for now and for maybe, I don't know, 5 to 10 minutes with independent observation. And then I will switch to the slightly trickier context of time series. So I will try to explain how to prove such inequalities and also what they are useful for, actually, how you might want to have such inequalities in statistics and in machine learning. They are very useful for actually applications. Okay, so the first well-known inequality for just a random variable, you assume that you have a random variable u. And actually, you know that if the variance of u is finite, then the probability that u minus its expectation in absolute value is larger than x is upper bounded by the variance of u over x squared. This is Chebyshev inequality. So a very basic one. And actually, what's nice is that if you want to use it to control the deviation of an empirical mean to its expectation, it's quite easy actually just to plug the empirical mean here instead of u, okay? And then it takes two lines, okay, to check that. So if the xi's are independent, their mean is mu and their variance is sigma squared, say, just to shorten notations. Then actually the probability that the empirical mean deviates from mu by more than x will be the variance of the sum of the xi's. But then actually the 1 over n becomes 1 over n squared, and the deviation here, x is x squared, as in Chebyshev inequality. The thing is that the variance of the sum here, because the variables are independent, is the sum of the variance. So it will be n times sigma squared, which means that in the end, you still have a 1 over n remaining here. So it's good because it says that actually when n is large, the probability that the sum deviates from, like the mean deviates from the expectation is quite small. But actually, on the other hand, this inequality is not this sorry, there is an inequality here. Of course, I just like it's a typo. There is an inequality missing in the first line, but this inequality is not tight at all, actually. And I will explain why this is not enough in most applications and why actually this is really far from tight. And actually the reason is something you all know. Actually, this is called the Galdon Board. And you probably saw such a thing in any science museum somewhere. So, you know, like you have a lot of balls and they move randomly. And then in the end, when they reach a place where they cannot move, actually they are distributed according to a normal distribution. And this is a visual explanation of something that you all know that's called the CLT, the central limit theorem. And I'm going to compare the CLT, the central limit theorem, to Chebyshев inequality. If you consider the CLT, it tells you that the mean minus the expectation, if you renormalize it by square root of n over sigma squared, it will converge in distribution to a standard Gaussian random variable. Okay, but the thing is that it has a consequence in terms of the deviations. The probability of a deviation of the mean to the expectation by more than x will converge when n tends to infinity to twice the CDF of the standard Gaussian, or applied to x times square root of n over sigma. And the thing is that this CDF cumulative distribution function of the Gaussian standard Gaussian random variable, well, it's a known function, and actually many of its properties are quite known. The fact is that actually it absolutely does not behave like that in 1 over n. Actually, the way it behaves is in exponential of minus n. So it means that Chebyshef inequality is a nice inequality, but it seems that it's quite not tight. On the other hand, we have something nice here, is that we have, of course, like in Chebyshef inequality, we have an inequality, an exact inequality here. While actually in the CLT, the deviation probability is only asymptotically equivalent to this quantity, but when n is fixed, you don't know actually how close you are to this asymptotic equivalent. So in some sense, the objective of the deviation inequalities I'm going to propose is to recover something that is close from the BAV or expected from the CLT, like in e to the minus n, but that will still lead to a non-asymptotic guarantee, that is to an inequality that holds for any n, and not after a certain very long time that I cannot know in practice. Okay. So in order to do so, the main tool actually usually is Chernoff bound. So Chernoff bound says that you are going to use Markov inequality, but not Markov inequality on the random variable u, but rather on the random variable e of a constant time u. Okay, so here you see exponential is an increasing function. So the probability that u minus its expectation is larger than x is exactly the same as the probability that e to the s times u minus its expectation is larger than e to the s times x. And then actually you use Markov inequality and you have this upper bound here. And what can you do with it? Well, it appears that if you do the same thing with here, instead of u, the empirical mean, so actually instead of its expectation, you have mu, then actually the expectation of the exponential, here is an expectation of the exponential of a sum, which is an expectation of a product of exponentials. And actually, thanks to the independence, the expectation of the product is the product of the expectations. So it means that if you want to have a control of this quantity here, then all you need to do is to compute this expectation of e to the s over n times xi minus mu for one xi. Okay. And a very famous result to do this is Hoeffding's inequality. So Hoeffding's inequality is just actually a lemma that was proven by Hoeffding on the path to proving all the results. But it just tells you that, for example, if u, capital U, is bounded, so actually with probability 1 belongs to a fixed interval AB, okay, then this expectation e to the exponential, the expectation of e to the s times u minus its expectation is upper bounded by exponential of s squared b minus a squared over 8. Okay, so you can now unfold, like plug this in the previous result and unfold everything and get a result. So actually, see, we started from the probability of the deviation of the empirical mean. We reached this product here, and actually the term inside the product can be controlled thanks to a mean inequality. And if you plug it back actually in the previous inequality, then you are left with a function of s, which you can optimize explicitly actually. So it's a two-line derivations. I did not do it, but you can derive this with respect to s. And it's just like something that's actually depend on s squared and s. So you differentiate, it gives you just a linear equation in s to solve. And the solution actually tells you this, that if the xi's are independent and bounded, so they belong to an interval like a, b, say -1 + 1, for example, then actually the probability that the empirical mean of the xi's minus mu is larger than x, so deviation from the expectation larger than x, is indeed in exponential of -2 times n times x squared over b minus a squared. So it's very important, because if you compare this to the previous result, now think again like about the previous results, Chebyshev inequality is only in 1 over n, but it's exact, it's not asymptotic. Then the CLT says that we should have something in e to the -n, okay, but it was asymptotic, when actually for bounded random variables, Hövding inequality tells you that you reach this e to the -n behavior in an exact sense. You have an exact here result and an exact constant, okay? So more generally, I just want to extend the previous results because it's something very useful for many applications in machine learning. And once again, I will explain this actually later. But actually, you don't have to only pay attention to means of random variables. Okay, so here 1 over n times the sum of the xi, it's a nice function, it's the empirical mean of the observations. But actually, you can consider instead any function of the observation, f of x1 to xn. And essentially, if this function satisfies that if you just replace one of the xi's by something else, then the difference is bounded. Okay, it's a property known as the bounded difference property for the function f. Then actually, you have exactly the same thing. The probability that f of the xi's is deviates from its expectation is actually, well, over n, sorry, here, is in 2 times the exponential of -n. Okay, and you see here the n in red. You still have this nice dependence in e to the -n. And just actually to confirm things, it's exactly the same thing as the previous inequality if you consider as a function the sum of the xi's. Okay, in this case, c is b minus a. Okay, if you change like if the function belongs to the range b minus a, and so in the end you just obtain actually that your McDermid's inequality becomes exactly Hövding's inequality. Okay, so in some sense it tells you that empirical means for bounded random variables are very close to their expectations. But also, it's not only empirical means, actually, it's all functions with this difference, bounded difference property that stay close to their expectation. And in some sense, actually, it's even the opposite in the sense that among all such functions f, the empirical mean is actually the one that for which the inequality is tighter. Actually, it's the one that has the biggest deviations in some sense. Okay, just one final remark. Many real-life random variables are not bounded. Okay, so if you consider like a Gaussian random variable, obviously the CLT that I reminded here will still hold. Actually, it's even exact in this case, but you cannot use Hövding's inequality. So many people wondered how to extend this result beyond bounded variables. And actually what you have to, in some sense, it's almost trivial, in the sense that what is important here was not the fact that Q is bounded. What is important is the result. we have that the expectation of the exponential moment of u is upper bounded by e of s squared times the constant. So why shouldn't I define a property that would be, I have a random variable u that might be bounded or not, I don't know, but the expectation of its exponential is actually upper bounded by e times s squared times the constant. And actually, it turns out that this is a well-known property, which is known as sub-Gaussian random variable. And it includes bounded random variables, but it also includes Gaussian random variables. And in some sense, it includes all random variables whose tails actually are decaying to zero at least as fast as the ones of a Gaussian random variables. And I will reuse this later, but it has many other, there are many other ways to phrase this property. And one of them actually does not refer to the exponential moment, but to the polynomial moment, like to the exponential of e powers of u. If they go to infinity, but not too fast, then actually you recover this. And so you will recover something very equivalent to McDermott's and Hövding's inequality. Okay, so that's it for the reminder. And now my objective will be to explain how to extend this for time series. So I'm still in part one, actually. I will explain what are the known, very briefly, the known things for the known results for time series. And then in part two, I will extend these results to new settings, actually, to non-homogeneous Markov chains for which these results are not always available. Okay, so if we come back to the objective, which was either to upper bound the deviation of the empirical mean from its expectation, or from more generally in McDermott's inequality for any Lipschitz functions of the observations minus its expectation. Then, but remember that now we are dealing here with a time series, not with independent observations. The very first step of our proof does not work. Okay, here you have the probability that the sum of the xt deviates from its mean. We upper bounded it by the expectation of the exponential of the mean, but that is expectation of the product. And for non-identical, for non-independent random variables, this will actually not be the product of the expectation. So of course, if you say that, anyone near you will shout and say it's wrong, and the cat will be very scared, and it's not a good thing to do. Of course, like the IID proof does not work at all. So first, no hope for this. So at least before I explain how what we can do, it's motivated actually a lot of work, and I want to say that it motivated a huge literature. So there are many papers and many books trying to prove such inequalities beyond the independent case. It started with papers on deviation bounds for mixing, probably in the 70s, and then actually people extended that to weak dependent time series, to Markov chains, to many kind of processes. I provided here just like random reference. Well, like for the paper, there are good, very good papers, but I mean, I just choose randomly among all the very good papers available. There are super paper by Emmanuel Rio, by Jérôme Dedeker, etc. I just wanted to advertise also for two books of my co-author on this paper, Paul Ducamp, because he's one of the specialists of this kind of theory, actually. Inequalities for dependent random variables. And we are lucky because he visited RIKEN just a few weeks before I joined, I think in 2019. He was supposed also to visit us actually in 2020, but unfortunately it was cancelled because of the pandemics. But like we have many connections with him. And fortunately he will visit again when it will be possible again. So anyway, I just wanted to say, don't expect easy answer like we had for the IID case. It's really an important domain of research, and there are some major difficulties at least for some processes. Now I will just comment on a paper because the proof in this paper was the basis. We extended it actually in our own paper. A paper by Jérôme Dedeker and Wan Fan, who is also one of my co-authors on this paper. And actually they focused not on all possibly dependent random variables, but on variables that would be actually sampled from Markov chain. And the Markov chain is of the form xn is S of xn minus 1 and around IID random variables epsilon n. Okay, I will provide examples later, but like essentially all Markov chains can be written in this form. And they provide deviation inequalities that are extremely close to the ones available in the independent case under the following contraction assumption, essentially that for a fixed epsilon, you see the same epsilon, but when x changes, then the function capital F, f of x epsilon n, f of x prime epsilon n, actually, in expectation over epsilon, will be controlled by the distance between x and x prime, where d is a distance in the space where x lives, and this with a constant rho in front that is strictly smaller than 1. Okay, so maybe before I explain our own results and before I provide actually an explanation of how this result can be proved, maybe I will explain briefly at least this rho smaller than 1. There are two options. If you are a probabilist or a statistician, you probably understand why. But if you are, I don't know, come from another background, it might be that actually the classical examples with rho equal to 1 that are not well behaved are not of use to you. So I want to show this on a very simple example. It's called autoregressive process. So in this case, x is simply a real valued random variable, and f of xn minus 1 and epsilon n is simply rho times xn minus 1 plus the random variable independence random variable epsilon n. So here you see that the contraction property that we had before is satisfied with rho, the constant. I mean, sorry, I should have decided to take, I should have written with absolute value of rho, but say that in this example, we assume actually that rho is non-negative. So it can be 0 or any positive value. Okay, so of course, like the property, the previous property is satisfied and not even in expectation. The epsilon vanishes here, and you see that it is satisfied whatever with probability 1 actually. I just sampled trajectories from this process, and you see that for rho equal to 0, xn is epsilon n, so it's just actually it's not Markov chain, it's just a sequence of IID random variables, and it looks completely random. What is funny is that for rho equal to 0.5, it does not change so much actually. Okay, there are little fluctuations, longer maybe than in the independent case, but overall, the two processes look quite similar. I mean, if I show you the plots of both, I'm not sure that actually just with your eye, without a statistical test, you could make a difference between both. However, when rho becomes closer to 1, there is a big difference. See that with rho equal to 0.8, you still have these fluctuations here. And these fluctuations, they are becoming a little bigger. So now I would say that everyone would be able to make the difference between rho equal 0.8 and rho equal to 0. Still, actually, on the long run, it doesn't make such a difference. The behavior is not so different from an independent process. But just when you reach exactly the threshold rho equal to 1, then actually the behavior changes totally. So this is known as a random walk. And it changes totally, like you lose some properties, the process can no longer be stationary. And actually, it explained in some sense, it gives a reason why we understand that actually the behavior here, when rho equal to 1, might be very different. Okay, in some sense, you have stationary solutions when rho is smaller than 1, but when rho is equal to 1, you don't have a stationary solution. So the variance of xn, for example, will cannot be a constant function in time. It will increase. Okay, so their paper covers completely this case as soon as rho is smaller than 1. Okay, so now actually this will be the end of the introduction. And sorry, it already took half an hour, but what we wanted to do is to study a case which might seem a little like a kind of pathological case, but actually it's interesting in many applications. And this case is when rho is smaller than 1, but is allowed to change with time. Okay, so we no longer have an homogeneous Markov chain. Okay, so careful, like homogeneous Markov chains correspond here to the case where the function f does not depend of time. Okay, so that was the case of the Dedeker and Fan paper. But here we studied the case where f depends on time. So actually the Lipschitz constant, the kind of Lipschitz constant rho can depend on time. And actually, interestingly, of course, in order to challenge the previous inequality, we want to allow this. Well, it has to remain smaller than 1, but we want to allow it to go very close to 1. So here, I just plotted an example. It's not the kind of example that is very interesting in practice, but it allows to see what the process looks like. I just did the same thing here, like autoregressive process, but I considered the case where rho n, instead of being equal to 0.5 or 0.8, is equal to 1 minus 1 over square root of n. So it's going to 1, but a little slowly. And you see that in the beginning, like from n equal to 0 to n equal to maybe 250, maybe we don't even make so much difference between this case and the case 0.8. Okay. But then actually, in the end, on the second part, it looks more and more similar to rho equal to 1, that is to the random walk. So the question was, is it possible to recover the same inequality than the Decker and Fan, which are actually the same inequalities than in the independent case, but in this case? Okay. So this will be the second part of the talk. First, so sorry for like if you already knew about these inequalities, then maybe the beginning was a little boring for you. On the other hand, if you have some doubts now or some questions, please interrupt me and ask questions. I have time, so otherwise I will cover now the after this like remainder of what is already existing. I will cover the contributions of our paper. Okay, so now what we changed. So I will come back to the Decker and Fan assumption. They had this kind of Lipschitz constants, and actually we wanted to allow the case once again where f will change with time, and rho will also change with time and maybe get close to 1. So actually, the assumptions that we actually used is as follows. So now I will give accurate statements. X is in, for now, any metric space, X with the metric D. But in all applications, actually, we'll have in mind, at least in this talk, we focus on the case where X is R to the D, but D is potentially large. It's not, what I did is not very clever because I used the same D for the distance and for the dimension. On the other hand, I think it will be clear from the context, but sorry about this bad idea. I don't think that the constants related to the dimension will be used so much in what follows anyway. And then the epsilon n RIID. So be careful, like as xn is a function of xn minus 1 and epsilon n, we have no reason to take epsilon n in the same space than x. Of course, if it's a sum, if xn is a constant times xn minus 1 plus epsilon n, then epsilon n lives in the same space than x. But I will provide explicit examples where actually we want to take y as a larger set than x. So epsilon n is in another space that is equipped with a metric delta. So we still have the Markov property. Xn is fn of xn minus 1 epsilon n, but this time fn, you see, depends on time. And then we have that the expectation of the distance in the x space between fn of x epsilon n and fn of x prime epsilon n in expectation over epsilon is upper bounded by d of the distance between x and x prime, but with this time the Lipschitz constant rho that depends on time t. So everything that will be related actually to rho n in what follows will be in orange. I hope it will clarify things and not just mess colors up. But okay, we also want to, sorry, we also require a control of the same condition, but on y and not on x. So like this time x is fixed and fn of xy, fn of xy prime has to be upper bounded by a function by tau n times the distance between 1 and y prime, and maybe plus a constant xi. So this condition here is also necessary. And by the way, I did not mention it, but they have a similar condition in the paper by Fan and the Decker. So it's okay. Here, we will also assume let actually tau n and xi n move, but they are less problematic, actually, I must say. Once again, the real problem, at least intuitively, comes from rho n if it goes close to 1, because in this case, you lose the stationarity as I showed with the AR process. For tau n and psi n, if they move, as long as they don't explode to infinity too fast or anything, but if they move, it's not such a big problem actually. Okay. So same convention actually I use for tau n and psi n, the green, and I will try to, I hope I did it properly on the following slide, but I will try to stick to it so that every property related to tau and psi will be in green. So an example, the first example that is actually used in economics is the generalization of the autoregressive example to multidimensional processes. So X is in R to the D. Here, so it's a vector, it does not have to be a real number. And Xn, so Fn of Xn minus 1 epsilon n is An, a matrix, times Xn minus 1, the vector, plus epsilon n, which is in this case indeed a vector in the same space than X. And to simplify things, for example, in some models, like you assume that epsilon n is actually IID from the Gaussian distribution. Okay, so two things. First, our conditions, we first had the Lipschitz condition here, but exactly as was the case here, actually, this condition is not even satisfied in expectation. It's satisfied with probability 1, and it's quite easy to check. You just write the difference of f with two different x's, and actually you obtain that the rho n that you have here is actually the operator norm of the matrix n. And so by operator norm, I mean like this, the supremum of anx of the norm of anx over the norm of x. Okay, and if once again, if you fix rho n and you say that it's a constant smaller than 1, then actually it's covered by previously existing work. But what we wanted to do is to check the case where rho n, the largest eigenvalue of A, is allowed to go close to 1, which once again is the case that was considered in economics and in econometrics. So for example, there is a quite famous paper by Phillips, about this like near integrated time series, quite an old paper now, but it's actually, there is a motivation in economics to study this kind of time series. On the other hand, here, if you check the Lipschitz constants, not with respect to x, but with respect to epsilon, then you see that actually trivially I missed the arrow. You see that the third condition here is trivially satisfied with actually tau equal to 1 and psi equal to 0. So as I said before, anyway, it's not so important in the sense that as long as you can control these by constants, whether this constant is 1, 2, 3, or whatever, it's not so problematic to n and psi n. The main difficulty is really in rho n. Okay. Now, this would be interesting because until now, actually, maybe there was not so much connection. I don't know, with the work of the high-dimensional modeling team. But now this here can be interesting when the dimension D is large and you want to estimate A under like sparsity or low rank assumptions, for example. That's a first case. Now a second case, I think, of application of our results, which is even of more interest for everyone doing machine learning, is actually stochastic optimization. You know, so we want to train a neural network, and you have L of X, that's your loss, your risk, sorry. So it's the sum of individual losses, Li of X. Okay. So X will be the weights of the neural network that you're trying to train. And in this case, you know stochastic gradient algorithm. So actually at each time step, you draw a set of M elements, capital M, but it's usually much smaller than capital N. It might be one element actually, but sometimes it's usually a mini batch. You compute the gradients or the subdifferential, assuming that Li is convex but not Lipschitz or whatever. But like usually, if you assume that Li is differentiable, you compute its gradient only, okay, on the mini batch, and then so in the gradient algorithm, you would take xn minus 1 minus a gradient step along like a rate times this stochastic gradient. Now, usually, if you are optimizing on a bounded set, if you want your weights to remain bounded, usually you had a projected step that is a kind of constraint that your weights do not go to infinity and that they remain in the bounded region of the space. So if you do so, then your function here is no longer linear. There is a projection here, but on the other hand, it will remain actually a kind of Lipschitz function of x. And you will see that it fits actually our setting. So here you see the randomness is no longer like the random thing we had, is no longer Gaussian random variable. It is a random variable here, the stochastic gradient. The randomness is in drawing capital M. So here it's really an illustration of the situation where epsilon, that is capital M actually, the set, the mini batch, it does not live in the same space than X. Okay.
So Pierre, sorry, there's a question from Sébastien Lousteau,
yes,
which is, so what will happen for discrete state space?
For discrete state space?
Yes.
Sorry, it was for the previous slide, not this one with the gradient. Here, for instance, if you have a,
the one before, maybe.
If we have a Markov chain in discrete space.
If you want X to belong to a discrete space?
Yes.
I mean, our results, like the general result you have, do not say anything about X being continuous or discrete. So as long as you have a metric that makes sense, which can be, for example, a metric induced by a graph, it might be the discrete metric, but I don't know if the results are fascinating in this case, but it might be like, a metric induced by a graph. Then actually this kind of process here, you will satisfy our inequality, no problems. On the other hand, here, I don't know, I mean, of course, you can have like kind of projections on a grid or something, but we did not cover this case in the paper, and I'm not totally sure actually about this case. Does it answer the question or?
Yes, yes.
Okay. So now in the gradient case here, yes, you have this function. And actually a generalization is the stochastic gradient Langevin descent, where you actually add a noise, a Gaussian noise here, that makes your stochastic gradient even more stochastic. Be careful, actually, maybe my notation is a little stupid, actually, sorry, because the randomness here is not only epsilon, the randomness is capital M, the drawing of the mini batch, and epsilon, which means that actually it's not compatible with the notation I have here. I should.
So sorry, Pierre, it looks like there is some connection issue.
Noise. So actually there are non-homogeneous Markov chains, but more importantly for our, like in this case, if you have some assumptions on the loss, if you assume that it is M, small m strongly convex, capital M Lipschitz, and that its gradient is also Lipschitz, which are strong conditions, but that's usually the kind of conditions people have to study the stochastic gradient algorithm anyway. Then actually we recover, for example, for FSGD, the conditions of our paper actually. So it's possible to prove that actually you see here you have a gradient step gamma over n to the alpha. Actually, if alpha is larger than 0, which means that actually your gradient step is decreasing to 0, then actually rho n will go to 1. So it's larger than 1, but it will go to 1 at the rate 1 over n alpha. Okay, so it's exactly our setting. It will go to 1, but it's not equal to 1. It will go to 1 at a given rate. On the other hand, if alpha is equal to 0, then essentially rho n, on the condition that you take gamma small enough, is bounded away from 1, which means that it's not a problematic case. It becomes an easy case actually to study. Now, of course, there is the Lipschitz kind of constant, Lipschitz or boundedness constant with respect to epsilon. But in this case, it's quite easy to check actually that your noise, like it's bounded. If you, thanks to the projection step that we have, like all these remain bounded with respect to the choice of the mini batch. So two different mini batches will give you two different xn, but they remain bounded at a bounded distance. So everything is fine, okay? For the stochastic gradient Langevin descent, you have here the epsilon in addition. So it slightly changes the value of tau, but essentially it remains the same because once again, I told you the difficulty is when rho tends to 1. If rho is bounded away from 1, as long as psi and tau remain bounded, we don't have so much problems. So here you just have to choose alpha and beta equal to 0 or positive. It's fine anyway. It's not what will be problematic for us. Now I can state our results, and I apologize for the heavy formulas, but I hope that thanks to the explanations before now, the results can be understood. Very generally, it's one of the results stated in the paper. Very generally, for any function that satisfies this difference, bounded difference condition, and among them you have the empirical mean. So actually we can use our result to control differences between empirical mean and expectations. Then actually you assume this condition that the distance between epsilon n and an independent copy to the power k has bounded moments. It might seem a little weird, but actually, sorry, I will change many slides, but if you come to what I said before, it just boils down to saying that the noise is sub-Gaussian, which we called actually this general condition, which is satisfied by bounded variables or Gaussian variables. So for example, Gaussian noise is okay. And it's kind of a general assumption, okay? So it sounds mysterious stated in this way, but it just says that your noise behave as well as a Gaussian. You also have to assume the same condition for the initial value of the chain. And then in this case, you have a deviation of f to its expectation. That is, well, there are many formulas, but I tried to use colors as best as I can. In any case, what you have is still e to the minus n. So it's nice because we are still in the same regime as with Hoeffding's inequality, which is the regime of the CLT, which is what we want and the best we can do asymptotically. It's in the e minus n. Now, there are two nice cases. First case, rho n is actually bounded away from 1. Okay, it's smaller than 1 or n minus rho, but sorry, it's smaller than, yes, 1 minus rho, where rho will be a fixed constant. So it's strictly smaller than 1, which is like strictly smaller than 1. So actually, it tells you that in some sense, in the AR case, for example, like you cannot have rho n going to 1. It might be going just to a constant, which is smaller than 1. In this case, we don't really have assumption actually on tau n and psi n. It's not restrictive at all. You recover the e minus c n exactly as in the IID case. It's the easy case, and in some sense, our proof, even though we wrote it down, but in this case, is quite equivalent actually to the proof of the previous paper by Dedeker and Fan. Now, a little more problematic could be the case where, but actually, if you enforce, which might be quite restrictive, but if you enforce that tau n and psi n go fast enough to compensate this, then you're still in the regime e to the minus n. So it's a case that might be a kind of borderline case. We have a difficulty coming from rho n, but tau n and psi n are nice enough to ensure that it's not problematic. Finally, if you, sorry, so actually you see that here the exponents in rho n and in tau and psi is the same, okay? So it means that it's a little restrictive in the sense that you have to be lucky enough so that the condition in tau and psi matches the one on rho. In a general case, when the condition on rho, like it goes to 1 at a rate that might be fast or slow depending on alpha, and psi n and tau n are bounded, but they not necessarily they don't necessarily match the same rate than rho n when it goes to 1. Then actually in this case, you still have an exponential of n, but it's not exponential of n, actually it's exponential of n to a power smaller than 1. Okay, so it means that you still have an exponential inequality. So it's better than say Markov, Chebyshev inequality, but it's less good actually than what we have in the IID case. So this is the case where actually rho n going to 1 becomes problematic. Okay, so I will just explain the proof, even though it will be quite short. I don't want to enter details. The proof, the beginning of the proof is quite standard, and I just want to mention it if you're interested. So the idea is to decompose essentially f minus its expectation as a sum of MT, and the sum of MT is just actually a MT is actually sorry, the sum of the MT is actually a martingale. So what you do is just you compare the increment, what happens when you condition with respect to x1 to xt minus what happens when you condition to x1 to xt minus 1. So you check how much actually the knowledge of f changes when you're just given xt in addition to x1 to xt minus 1. And actually what is nice is that then actually the conditional, the Chernoff trick that I presented before, even though it doesn't work as is, you can slightly adapt it so that it will work in the almost as in the IID case, because the exponential of the sum of the MTs, you can split it in two, the exponential of the sum from t to n minus 1, and then separate actually the exponential of MT, but condition this with respect to x1 to x minus 1 thanks to the Tower property of the conditional expectation. And then actually, thanks to the Lipschitz conditions that we have, then actually you can control this part, the exponential of E of Mn given x1 to xn minus 1. And these are calculations that are a little similar to the one in the IID case, but here actually it requires more care because the variance of Mn will highly change with time, actually, because of the non-homogeneity of the chain. So in order to provide a control of Mn here, it requires some work that is a little painful derivation. Then actually at that point, there is no very, how can I say, very deep concentration tools anymore, but it's quite a heavy calculations, I must say, to derive this. Okay, now I will advertise for the paper. So sorry, I just presented actually how to derive one exponential inequality here, which is kind of extension of Hoeffding inequality to these Markov chains. But actually in the paper we have like McDermid, Hoeffding, and Bernstein inequalities for this. And then actually for the case where epsilon would not be sub-Gaussian, so for example, if epsilon has a variance but does not have a very high moment, it does not have a moment of order 1000, then you will not be able actually to derive a Bernstein inequality, but you still can have semi-exponential inequalities like Fukunaga-F, or moment inequalities like Marcinkiewicz-Sigmund. So for example, like Marcinkiewicz-Sigmund is an inequality on the deviations that comes back to polynomial things. So if you use it with a square moment, then it will actually boil down to Chebyshev inequality. So these are weaker inequalities, but under weaker assumptions. I will, sorry, I don't have any more things to, well, like a lot of things to present, but I just want to present two applications. They are not very developed, but I assume that I already threw a lot of formulas. So I just want to provide the idea. First, if you're dealing with time series and you want to study the performance of an empirical risk minimization procedure, actually, usually what you do is that you consider the empirical risk, that's the sum of the loss of theta and the observations xi, and you want to minimize it, but the question is how close is it from its expectation? And there is a well-known theory for the IID case, which relies actually on deviation inequalities. So our results here tell you that the risk and will deviate, like the empirical risk will deviate from the risk by a given quantity, not often. The probability is upper bounded, even when the xi's are not IID, but are a Markov chains. So that's for one given theta. And then if you use it for learning, then you have to do like union bounds or that kind of things to try to recover results. So I don't have time to, and I did not plan to cover details for all situations. Like if you have, for example, finite parameter sets, capital theta, so you want to choose between a given set of classifiers that is finite, you minimize the empirical risk, and you know that the true risk will be smaller than the minimum of the empirical risk plus x. And with a union bound, actually, you obtain this capital N times E minus C small n. So these results are, of course, once again, well known when you are working with IID data. But in any case of Markov chains, actually they were known maybe for the first line that corresponds to the case where row n is upper bounded by 1. But actually, thanks to our results, you can upper bound this to the case where row n will tend to 1. Okay, and obviously the techniques used to cover infinite parameter space theta can be also adapted to this time series setting, but it's not, there's nothing specific to time series there. So I did not want to cover actually this part. You can, for example, discretize the parameter set, and actually if it has a finite covering number, then you will recover the usual rates actually. So it's the kind of things that you can do. The other application actually, so that's the stochastic gradient and more generally stochastic gradient Langevin dynamics. So here you study this, and at the end of the iterates, actually you take the mean of the xt's that you generated so far. Okay, and a direct application of our results says that for example, in the case where alpha, so alpha is the exponent here in the learning step, is between 0 and 1, as long as you don't choose the other constants in a pathological way, actually, then xn bar, so that's in the end your final estimate of the minimizer, will be close to its expectation in the sense that the deviation in p norm here will remain close to x with probability close to 1. So the probability that it deviates from more than x is in exponential of minus n. Okay, so it only tells you how close it's xn bar from its expectation. Now the thing is that the literature on stochastic gradient already took care of the expectation part. And this is actually why our result is useful, is that most papers mostly focus actually on the expectation part. And for example, there were results like first in a various, like with various assumptions on the function, etc. But like when it comes to taking alpha, maybe I did not write it. I think that you have a constraint here on alpha. Actually, like there was a very nice paper, sorry, by Moulin and Bach, where they proved that for alpha equal 1/2, for example, for the strongly convex case we're studying, then you recover the expectation of xn bar minus x star is in squared, sorry, is in constant over n. It's not the only results. There are many results like that, but I chose this one. And then if you combine, actually, so this will give you a bound on the expected distance between xn bar and x star. And so if you combine this with the fact that xn bar remains close to the its expectation, then you obtain in the end something that is more powerful actually than simply the result in expectation. You know that the distance between xn bar and the true minimizer of your function, x star, in Euclidean norm is roughly in 1/n with large probability. Okay, so it's deviation results that is stronger actually than simply the result in expectation. And that's it. So I want to thank you for your attention. And if you have questions, I will be happy to try to answer the best I can.
Thank you very much, Pierre, for your very instructive talk. It was very nice. So if people have any question, please feel free to ask, to shoot questions.
Maybe one question. Pierre, can you go back to the value of rho for the SVD case?
Yes. Here, yes.
Here, okay. So it seems to can you detail the link with, for instance, in optimization, the learning rate schedule? Because here you have a learning rate.
Yes.
So order gamma over n alpha.
So exactly. So actually, you have many things that were studied. You know, like depending on the context. Of course, it also depends of whether you are doing stochastic optimization or deterministic. But if you are doing stochastic, people consider the wide range of values for alpha, usually between 0 and 1. Okay. Including including the case alpha equal to 0. That would be like a constant learning rate.
Yes.
Or alpha that would go to the alpha that would be larger than 1, which means that in this case the learning rate gamma over n alpha goes to 0. Okay. So yes. Here all this is covered here. So basically, if you take a constant learning rate, it's the easier situation for us because it means that you are considering like a kind of autoregressive process. Okay, so rho n is equal to a constant, and on the condition that you choose gamma small enough, actually, then this constant is smaller than 1. So it means that if you go back to our inequality, maybe where was that? Here, it's a nice case for our inequality when the case where actually rho n is a constant. So you are in the first line. So it means that in terms of deviation, it's a nice choice. On the other hand, it might be that it's not a nice choice in terms of the other part, in terms of the expectation. Okay, but in terms of deviation, it makes life easy. Now, if you take alpha larger than 1, then you are, in this case, 1 minus n gamma over n alpha, which takes you in our theorem to the second or the third line. And actually, what is important in some sense is to try to target the first line, because if you target the second line, it means that you are, in a situation where the deviations will be larger than in the IID case. So you will, essentially what will happen is that your rate will no longer be in 1 over n here. It will be smaller, maybe 1 over n to the 1/4, okay? So this actually is, might be in conflict with the alpha that you want to choose that you want to choose here, but actually it's not the case. So Moulin and Bach, I think, I will come back once again here. They studied the case. They proved that actually, if you are in the second, essentially in the second line of our results, then for alpha, so I cannot remember if alpha is larger than 1/2 or smaller than 1/2. I just forgot. It's just something to check in their paper. But it's essentially, actually, the results, which gives like a fast convergence rate in expectation, is also compatible with our deviation inequality. Is it clear? Sorry.
Very nice. Yeah, very nice. Thank you.
Thank you.
Thank you for your question. So is there any other question?
I have a question. It might be a bit silly. You were talking about the bounds on SGT and SGT at one point, and you said the randomness was in the selection of the mini batch, and I didn't quite understand what was the, I mean, I understand that there's randomness in the elements you pick, but how did you model that, or did you don't model it? I didn't understand.
Sorry, so referring here to the choice of the mini batch, capital M.
Yes.
The problem is what? Sorry, is how I take care of it in the proof, or how I missed actually the last part of the question.
I was wondering. I mean, I just didn't understand because it's like maybe interested in is modeling the variance in my deep learning in the convergence, and I was wondering, how did you model this? So if you modeled it.
So no, so I mean, if I want to be clear on this, if your question is, can you use our results, for example, to optimize with respect to the mini batch size M, then I would say that our results are not tight enough, from what I understand. Here, the bound we have, here, for example, essentially, we say the gradient can take you, the stochastic gradient can take you anywhere. But in the end, as we go through projection, then actually xn, whatever is your choice of the mini batch, here epsilon n, the value of xn that you will choose, they always belong to a bounded set. So this makes the result a little rough. And here you see it because psi n is upper-bounded this by a constant m. And sorry, like I did not pay attention again to conflicts of notation. This constant m is the m Lipschitz constant of the loss. It's not the size of the mini batch. So actually, in some sense, we took the worst case and did not pay attention to what could be the variance induced by your mini batch. So on the other hand, I want to say, maybe it's possible to refine it with our paper actually. So if you go here to this part, you see that of course you expect that the variance of your gradient will depend on the size of your mini batch. And then actually you can maybe try to do a better work here. I'm not completely sure though, because this might be like the weakness of our result here, is that you see that the Lipschitz condition on with respect to x can hold in expectation, but the Lipschitz condition with respect to the stochastic, to the IID part, like the mini batch, has to hold almost surely. So I would say that our method here cannot work to improve psi n, which means that whatever the mini batch size you use, psi n will be a constant. It will not depend on the size of the mini batch. So I don't think that our result is tight enough to guide you to the choice of the mini batch. But maybe on the other hand, it's possible to slightly improve this result to get to this point. I'm not sure yet.
Okay, thank you very much. It's very interesting. I don't usually have this point of view, so it's very interesting. Thank you.
Thank you.
Thank you, Peter. So maybe just one last question. Maybe Pierre is a you've talked for a long time.
No. I'm
you.
just...
Then can I ask one question?
Yes, of course.
So yeah, thanks for that nice talk. It's very, very nice. And so maybe someone related to the previous question. So is that possible to use this bound for the graph neural network analysis? Because if we train the graph neural network, it depends on the the edges connected, and then so the samples are not IID in that sense. I just wonder whether we can immediately use it or still there's some gaps between.
So the samples are not IID, but would they have a kind of a Markov condition or?
Okay, there's no Markov condition.
I mean, definitely in this literature, not in our paper, but if you go back to the literature, general literature, people studied dependence not only for time series, but also for fields, possibly, for example, or for many situations where you don't necessarily have a Markov condition, but you can have other dependence conditions. So there are many results for dependent variables. It might be that actually a kind of graphical dependence like that would be covered in some paper, but really for our paper, the temporal Markov dependence is crucial.
Okay.
But,
I see.
Maybe,
yeah,
maybe the reference section of our paper would be more useful than our paper itself for this question.
Okay, yeah, but anyways, it's very, very nice talk. Thanks.
Thank you. Thank you very much. And once again, the slides are on my webpage, so just feel free to download them. And if you have questions later, you can just ask.
Thank you very much, Pierre. So I think we can. We'll have also a lot of questions, so we can maybe discuss when we meet next time.
Okay.
Well, so I think we can conclude today's seminar. So once again, thank you very much, Pierre, for this very instructive talk.
Thank you.
And to show the potential applications. It was quite nice. Thank you very much, Pierre.
Thank you. See you later.
And thank you everyone for joining also the seminar.